Okay, those of you that watch the shows, what we're doing is the 2.4 worksheet. We're just checking our answers. Okay, so I got that typed in. Now let me get these in. Oops. Leave off 85, 71, 90, 82, 26, 62, 91, 45, 60, 78, 25, 36. Seriously? Oh, that's the problem with this data set is you can easily type things in wrong. 76, 91, 89, 84, 85, 33, 83, 87, 42. Okay, good so far. 94, 67, 94, 85, 71, 90, 82, 26. This should be 86 and 86. I missed the 386s. I think I got my mistake. And then 76, 76, 67, 67, 62. Okay, so when I do that and do my y1 till the mx, nope, mx1 plus 1 plus b, do I get the same thing as you? So this is what I get for the slope and the y-intercept, which is a little different than what you had. Is this what you did to get your answer?
No.
Gotcha. What did you do?
I just picked a couple points on the data set and just kind of I picked a line that looked like it fit best.
Got you. So anytime I ask you to do this, well, so first let me back up a second. This time I told you which one to pick. I said line of best fit. But anytime I say that, Desmos is your tool. So I'm never gonna, in this class, I don't ever ask you to do anything by hand. Although the textbook did ask you to do it once. I didn't have you do an exponential model. Here is one. Is it any better? Nope, it's worse. But you should always be doing, for any data set I give you, you should be doing this for linear and this for exponential and deciding which one is best, except for 2.4. I told you which one to do, line. Does that make sense?
Yeah, so what is that equation again? It's just y equals mx plus b, right? Or
yes, but notice this special symbol. Think of this as like typing a code into Desmos. So this tells Desmos, do this regression thing. And then the y subscript 1 and the x subscript 1 are there because the table is labeled as x1, y1.
Okay.
So if the table had been x2, y2, we would do y2, x2 in here. And the m and b don't matter. It's just that the way we learned it or the way the textbook wrote the general equation of, or the point slope intercept form was with an m and a b. So I'm just trying to be consistent.
Okay.
That's for linear. If you look at 2.5, no, 2.5 isn't, we don't. If you look at the 2.6 worksheet, where here I say find a regression equation, there you're going to do both. And the better one is the one that has an R value that's closer to 1 or -1. I think this one was exponential.
Okay. And the exponential one is y equals ab x raised to 1.
Yep. And so you're going to use the tilde in there, and you're going to use the ones provided that's what is in Desmos for your table, as long as those match.
Okay. Can I see that exponential one real quick?
Yeah,
oh, there it is.
Or there.
Okay.
Maybe it's better to see the Desmos one, right? I don't know. Oh, now you can't even see it. There we go. Oh, there.
Sweet. Okay, cool. That'll help out a lot.
Good, good. And on the midterm, you are doing this very thing. A couple of times you're gonna be given a data set and you're gonna figure out, I think there's two data sets, probably one is linear, probably one is exponential. Just in case anyone's forgetting, this R value here is the correlation coefficient, and that's what you look at to determine which is the better model. Also with exponential, don't forget you have to click log mode to have an R value to compare between the two.
Okay, cool, because I did forget that too. So R is the correlation coefficient, and you have to click log mode for
exponential to be able to see it. Yes.
Okay.
Awesome. So if we go back to 2.4 B, where it says state the correlation coefficient, that's literally just, hey, what did Desmos tell us? And for that problem, it's 0.4913.
Okay.
It says 2 decimal places. So that's all I'm looking for there. And there isn't any interpreting of R. It's just, hey, this is close to 1, so that's the better model. Although in this case, this is far from 1. So this model is garbage, which is what you're talking about down here. Cool.
Okay.
Good question.
Thank you.
You are most welcome. Anyone else got questions? Okay. Oh, Mike, you said 2.5. 2.5 is different than this. Was there a particular thing on 2.5 you wanted to look at, like on this page, or were you good?
I think the exponential part of it, I'm going to pull it up real quick. I think I was doing the same thing that I did for the other one. So I think once I do what we just talked about, I think that'll help me out.
So for this one, yes, you can do that. But for numbers 1 and 2, you don't need to write an equation. You're just figuring out the slope and the y-intercept and the growth/decay factor. But you make a good point. You can actually, once you put these data values into Desmos and run this regression, it will tell it to you. So you can use the calculator to find these things if you want.
Because I know we went over this one on Monday, and I think it was y equals 1 times 2 raised to the x.
Nice.
But I don't know why that is exactly. I'm still kind of having trouble with it. And the 1 times 2, I think, is the slope, right? 1/2.
Well, for the exponential thing, there is no such thing as slope. That's only applies to linear.
I mean the growth.
Nice.
/
Yes.
decay
Okay.
factor.
So generally speaking, our little formula is this: y equals ab to the x. So this thing we write as 0, a, and that's the y-intercept. And the thing that has x as its exponent is the growth or decay factor. So if it's greater than 1, we call it growth. If it's between 0 and 1, we call it decay.
Okay, so then would it be 2?
So 2 is a number greater than 1, so this is the growth factor. Yeah, b equals 2, and it's growth because it's larger than 1. Yep. And we found that by these points that we had here. So 0, 1, 1, 2, 2, 4, 3, 8. And we just noted that we multiplied by 2 for each one of these to get the next value.
Okay.
That's one way to find it. The other way is if you type this table in Desmos, it'll spit out this exact equation.
Okay.
And actually, this is how I created this graph when I made this problem. And this one, it doesn't matter whether you do log mode or not log mode because it's perfectly exponential. So there's your two parameters, A equals 1 and B equals 2.
So when you type that into Desmos, it finds automatically the slope and all, and the growth and decay factor for the graph, for the data set that you put in.
Yep. As long as you know how to read it.
Okay.
Yep. Excellent. Excellent. Okay. Anyone else have questions? Now that I've closed that. Let's see. I just saved this thing. Here we are. Here we are. Okay, so today we're doing lesson 3.2. Tuesday we did 3.1. What is it? What is it? Monday? Good gravy. So what we're looking at in 3.2 is now compound interest. So what I'd like to do is quick remind us of what we learned last time. So what we learned is all things simple interest. There were two formulas. So there was just the interest formula, which is I equals PRT, and this calculated interest after T amount of years. And then there was the future value formulas, and there were three versions of them that we had. And it was A equals the principal plus the interest re-earned, which is this, or A equals the principal plus the principal times the rate times the time, which is replacing this I with this, or there was the one that, whatever, it was this one, 1 plus RT, right? And then we did a bunch of different work with this one where, like, hey, we said, if you know the interest and the principal and the time, what's the rate or whatever. I didn't show you this, but I could solve each one of these for those other things. So if I want to know the rate, I would just divide both sides by the principal and the time, and I could rewrite this formula as this. The rate is equal to interest divided by principal times time. Likewise, time is equal to interest divided by principal times rate. And then what's the last one we need? Oh, the principal, the less common one, is equal to the interest divided by the rate times the time. So in the textbook, we did like algebra. We used this equation first and then substituted in the things we knew and solved for the other thing. But we could just rewrite this equation into its other four forms and just solve and just plug things in. You don't have to. You can stick with this. It's up to you, whatever is easiest for you. So now we're going to look at compound interest. So we're going to add a bunch of new formulas, although there's not that many new ones. So I'm just going to list that here, and we're going to figure these out. So, let's see. My wealth has come from a combination of living in America, some lucky genes, and compound interest. Warren Buffett. I don't know if you know about him. They call him the Oracle of the Midwest. He owns Berkshire Hathaway Company. He's made billions of dollars. He's a very wealthy man. From what I've heard about him, he lives a very simple life. Like he lives in a pretty standard house and drives old cars, whatever. Okay, so this is a review of what we did last time, where with the simple interest, we had that we invested $600 at 5% interest, and we recall that 5% of 600 was 30, and for simple interest, that's fixed, right? So you earn $30 each year, and that's it. And then right at the end of the section, we looked at, well, what happens if we had reinvested the $30? What happens if we earned interest on that? So that's what our author is asking us to do here. Compute the amount of interest earned during the second year if that amount is 5% of both the principal amount, the 600, and the $30 interest. So that means we're being asked to calculate 30% or 5% of $30 and add that to the 30 we already got. So I'm going to do 30 times 0.05, and that means it's $1.50. So if we do that, really after 2 years, we would have the $30 we get off of the $600 plus the $1.50 we get off of the $30, and we should be adding $31.50 to the total. So instead of $60, we'd get $61.50, and the new ending value would be $661.50. So authors like, well, wait a minute, why don't we use the I equals PRT formula like we did with simple interest before and just use a new P, the 630. So instead he's saying do this. 630 times 0.05. How much interest is that? Well, guess what? 630 times 0.05 equals 31.50. Well, that's what we already did, right? Calculates it directly. We did 1.5 plus 30 to get 31.50, added it to the 630. We got the 661.50. Yeah, these are the same thing, right? Okay, so let's fill out the rest of this. So we know after 1 year, simple interest and compound interest are still the same. If it's compounded annually, we get the same amount of interest. But after the second year, we added $1.50. So we got $661.50. I'm sorry, $61.50, and this became $661.50. Now, to get the amount of interest we're going to add to the $61.50 for the third year, we have to take 5% of this of the new balance at the end of the 2 years. So we're going to do this thing. Am I recording this? I think I'm recording this, aren't I? Yes, I'm recording. Good. Am I? I am. Whew, okay. So now we earn $33 and 0.075 cents, almost 38 cents. So we're going to add that amount to the 61. Oops, 61.50. And we get 94.575. I'm going to leave in that 0.5 cents, right? So this is the new total amount we've earned. We then need to add that to the 661.5, and we get 756.075. How are we doing so far? All right, all right. So repeat, right? Rinse and repeat. 756.075 times 0.05. So take our new account balance, multiply it by 5%. Oh, we're going to earn now $37.80, and then like 375, what is that, 100,000ths of a cent. Add to that and it's 94.575 from the previous years. And after 4 years, the total interest we would have earned is 132. I'm going to round now, 0.38. Add to that 756.075, and the new account balance is 888.45. Boy, what did I do wrong? Feels like something happened here. Oh, right. I'm supposed to add this 132 to 600, not the previous balance, because that's a total interest earned off of the whole thing. I'm sorry. So our real answer here is 732.38. No, what? Oh, I did this one wrong too. Sorry, y'all. So this is the total interest earned after the 3 years. So I need to be adding this to the original amount, not the previous year's balance. So I really screwed this up big time. So this should be 694.575. And then I need to do a new calculation, 694.575 times 0.05. So really we're adding 3473. So it should be 129. Yikes. Okay. Does that feel better, or did I just make things worse? So this should be 729.30. All right. How do you feel? I was adding this to the previous amount instead of adding the total to the initial amount, which it was giving us more interest than we were actually earning. So if you look at the prior amount, it was 720 for simple interest. For compound interest, we're at 729.30. So the difference between those two is $9.30. Not a ton of interest, but still it's more, right? So if we did this for a very long time, we would end up having a huge difference between the two. So let's create a nice compound interest formula. Now the author does this interesting thing. He says, take a look at what we did. We did 600 times 1 plus 0.05 to get the first future value using this P times 1 plus RT. This is why he wanted us to know this formula. So I'm going to write this out because I think seeing it already written out, it's a little bit confusing. So our first calculation is 600 for the future value times 1 plus 0.05. And that got us the 630. So then what we're going to do, or what we did, is we took this. So this is year 1. Year 2 is we did this, multiply this thing by 1 plus 0.05. Well, if we think about what this 630 is, it's this 600 plus 0.015. So really we're taking the initial calculation we did and we're multiplying it by a second one of these. Well, this is equal to the 661.50. How are we doing so far? Maybe I should be showing these, how this gets calculated out in Desmos as we go as well. So here's a 600 times 1 times 1 plus 0.05. So 630. Here's a 600 times 1 plus 0.05 times 1 plus 0.05. 661.50. And it turns out with exponents, remember, if you multiply by the same thing more than one time, you can write it as an exponent. So this is really 600 times 1 plus 0.05 squared. That's the same thing. Well, if we go for year 3, this whole thing represents year 2. So we're actually just going to take that and multiply by another 1 plus 0.05. And that gets us the third year. 694.575. In other words, this. Okay, so now I think we're ready for the formula. What if we did T years? Our formula would become 600 times 1 plus 0.05 raised to the T power. That's it. And then we can put any value in there we want, and we can figure out how much interest has been earned over that time frame. In other words, here's the compound interest formula for something that's compounded annually, once per year. We take the principal, we multiply it times 1 plus r raised to the T power. A nice handy little formula. So let's apply it to a particular, let's apply it here. Here, we're going to do the same $600. We're going to earn the same rate, 5% interest, and we're going to compare the amounts after T years. So here the formula is 600 times 1 plus 0.05 to the T power, where this is T. And for simple interest, it's 600 times 1 plus 0.05. And here's the tricky part. T is inside the parentheses, right? Desmos is great for putting these together. So in Desmos, I'm going to create two functions. F of x is the exponential one. So that's 600 times 1 plus 0.05 raised to the x power. And then g of x will be the simple interest one. And that's going to be 600 times 1 plus 0.05 times x. And then what I'm going to do is I'm going to create a table. And I'm going to put in here f of x1 and g of x1. And then I'm going to put in these values that we're asked to find. 10, 20, 30, 40. And the table, because of how I set this up, it'll spit out each one of those values for us nice, really quickly. There it is. So after 10 years, the compound interest one has $977.34 in it. And the future value only has the simple interest only has $900. After 20 years, you can see we're looking at 1591.98 versus 1200. After 30 years, 2593.17 and 1500. And then 4223.99 versus 1800. Now, what I love about function notation is we can calculate the difference between these two, and we can say, well, how much more are we making each year for the compound interest versus the linear. So I'm just typing in here f of x1 minus g of x1. It's just subtracting these two numbers. And look at that. The amount of extra interest we're earning over time is just, it's getting bigger and bigger and bigger, which should make a lot of sense, right? So if we do 50 years, we're up to 4,000 and 60 and 70 and 80. I mean, we're all probably dead by this time. but still it's fun to see what happens to that number. Eventually, like it's insane amounts of money. Like we're looking at we're looking at $1 million difference. Yeah. So first I typed in these two functions. So I typed f of x and g of x with the exponential one first. So here's the exponential or the compound interest one. And then this is the simple interest. And then I created a table, and I noted in the table that this was labeled as X1, and I want to evaluate f of whatever numbers I put in here. So I type in here f parentheses X1. And then I also want to evaluate g of X1. And then I want to see the difference between those two. So f of X1, whoops, minus g of X1. Is that good, Jennifer, that piece? Okay, and then we just put in our numbers, 10, whoops, and it auto populates for us, 10, 20, 30, 40. Okay, you are most welcome. Good. So back to the textbook. So clearly exponential or compound interest is way better than simple interest. I mean, we already knew it, but whatever. Oh, we were supposed to look at a graph of these two. So let's go ahead and look at our graph. I'm going to do zoom fit. There's our two equations. You hopefully from unit 2, it's very clear which one is the linear one. It's the purple one versus the exponential, the green one. And then you can see the differences are also exponential growth. I wonder if we could do that. I wonder if it'll, I'm curious. I want to see if we can make a model. Out of those. Oh, did it do it? No, it can't handle that because of all that mess. Okay, never mind. All right, so that's our graphs. You can see that over time, the difference between these two gets insane. And we already noted that here when we calculated the difference. After 40 years, like if I type in x equals 40, this distance between these two numbers is $2,000. And when we get up to, say, 200 years, that distance is crazy. Here's the 200. We're like $10 million difference. This is how you do generational wealth, right? So you get some sort of investment that gets a 5% return on your interest forever, and then your grandkids or great grandkids are living off of that interest. I wonder if that is enough money, like if this is an annual interest you're making, if that would be enough to draw a salary off of, like a monthly salary. Okay, so that's our graphs. I would like for you all to try this problem. I'm going to do 5 minutes. I want to see if you can calculate the simple interest and the compound interest on this thing. How much money, how much interest did you earn for both? And this is a trick question, all right? So be careful. So I'm going to give you 5 minutes to try that. Set a timer for 5 minutes. You'll do okay. So for the simple interest, I get that you earn $24,000. For the compound interest, I get that you earn $126,247.696. Is that correct? Have we answered the question? Nice. Now, I'm trying to trick you all because this is a thing. This is a problem. Oh, okay. I just need to give you some more time. I'm sorry. Oh, that's not what I wanted to do. So there's a problem between these two. Because over here, well, why are these numbers so far apart? Let me ask you that. Why are they so different? Well, let me talk you through this. There it is. Oh, wait, we have an answer. Yeah, one is the 100,000 in it, right? So this number here, this is a future value, meaning account balance, where this is just interest. So if we want to calculate interest in the compound interest formula, we have to subtract the principal. So it's, in other words, interest is A minus the principal. We don't have a way to directly calculate the amount of interest we earned in a compound interest scenario. So really the answer here is this thing minus the 100,000. Awesome observation, Mike. And there's the difference between the two. So really we only earned an extra 2,000 for the compound interest compared to the simple interest. So this is another little formula we're going to add to our list of things here in a second. Okay, now lots of times interest is compounded more often than once per year. And what we mean by compound is we mean the amount of money that gets deposited into your bank that we then earn interest off of. So most often banks compound interest monthly. At least the ones I look at, the ones I use Capital One for my banking needs, and they deposit every month a portion of the interest into my account that I then get to earn interest off of. So that's what this second part is getting at. So here we're saying, let's say that interest is compounded 4 times per year. The language for 4 is quarterly. So if we have our $600 investment at 5% interest, the banker would not add 5% to the account 4 times per year, because then you'd be getting more than 5% interest. It'd be a much higher rate. Instead, they take the 5% that they would have given you and they divide it into 4 different parts. So every 3 months, wait, where did the 3 come from? Let's see, 12 months in a year divided by 4 times per year equals the 3 months. That's where that came from. So every 3 months, they give you a fourth of the 5%. In other words, they're giving you 1.25% every 3 months. So here's how we would calculate that: 600 times 1 plus the interest rate divided by 4. What do we get? Desmos knows. Ooh, I need parentheses. 1 plus 0.5 divided by 4. So after the first 3 months, they would deposit $7.50 into our bank account. Now, what would it be after 6 months? Well, after 6 months, we've done another quarter, right? Because this is the first 3 months, and then the next 3 months would be another quarter of it. So 6 months is halfway through. So we're going to multiply this amount by 1 plus 0.05 divided by 4. What do we get there? Well, let's have Desmos do it. So I'm just going to add in here another 1 plus 0.05 divided by 4. Oh, now we're going to have 615.94 into the account. Right, so we added another little portion in there. If we want to know how much interest, we would subtract the 6,750. We might as well. 615.94 minus 607.5. So in that, ooh, 615.9. Okay, come on now. 615.94 minus 607.5. We now added in 844. Where did that number come from? That was 0.0125% of 750. That was another $9.09. That got added in. Oh, come on. So the extra we earned was 94 cents. By the time the first year is up, we would have multiplied by this 4 times. So the exponent outside of this, we would do 600 times 1 plus 0.05 over 4 raised to the 4th power, and that's the amount for 1 year. So the total exponent would be 4, which is the number of times per year that that interest has been compounded, right? So these two numbers are matching. What if we were compounding monthly? Well, that means each year we would compound it 12 times. And then if we did that for 5 years, each of those years would be 12. We would be adding together 12 5 times, or 5 times 12. We would have compounded the interest 60 times. Well, what if we decided to compound any amount of times we wanted per year? Let's call it n, and we did it for t years. Then we would be doing it the n times t amount of times. So our formula for this problem would become this. This is how we can calculate the amount of interest earned. Actually, it's the future value, not the amount of interest. The future value on an account that gets compounded n times per year. If you've ever read the fine print on your credit card, this is what they do. They charge you a daily interest rate. And so they compound the interest on your credit cards daily. So they take that APR and divide it by 365 or something of that nature. And that's how much interest you get charged each day. Okay, here's the general formula. The principal, the rate, the compounds per year, and the time. So let's do a practice problem. I'm going to ignore this one. We're going to do this one. Find the future value of the 600 investment at 5% interest, compounded monthly and compounded daily. We're going to use 365 for that. So I'm going to label these n equals 12 on this side, n equals 365 on this side, and I'm going to write out my future value formula. So A equals the 600 times 1 plus 0.05 divided by 12 raised to the 12t. And then over here, I'm going to write a second one. A equals another one, 600 times 1 plus 0.05. This time we're dividing by 365, and we're raised to the 365 times t power. So what we want to do is see, like, how big of a difference, like how much extra do we earn here? So I'm going to do the same thing in Desmos that I did with the simple interest and the other one that I did here. Instead, I'm just going to make two functions, one for monthly and one for yearly or daily. I'll use f of x for monthly. Oops, I don't want to use t, I want to use x. I wanted to say note. And then I'm going to put create a table. We're going to do f of x1, g of x1, and we'll start with and then I think I also want to do the subtraction. So f of x1. Well, actually, the g of x is going to get us a little bit more money. So let's make it so it's positive. Let's subtract the f of x from the g of x. So we wanted to know how much is it after 1 year. Well, it's 6 cents extra in 1 year. All right, how about 10 years? Oh, 99 cents extra. How about 20 years? Oh, $3.27 extra. How about 100 years? $800. How about 1,000 years? Whoops, I did 10,000. Oh, 1,000 years is a huge difference, but no one lives for 1,000 years, right? Well, let's do 200 years. Note that there is a difference, but it's slight. Even after 100 years, which most of us are probably dead at that point. Like, I'm not going to make it to 139, I guarantee it. It's only $800. So it does, the amount of times you compound does make a difference. It just doesn't make a ginormous difference. Okay. That's what number 7 is. Draw a general conclusion. So in increasing the number of compounds, increasing the number of compounds per year slightly increases the amount of interest earned. All right, so there's another little thing here we're going to talk about right now, and that's called the effective interest rate. And this little formula helps us compare different compound interest rates. So, you know, the author says we've seen that the number of times interest is compounded per year has an effect, but how much interest is actually earned? It's not a huge effect, but it is important, especially if you're borrowing. So this is a nice little formula that allows us to compare various compound interest rates. And so the effective rate, which is also known as the annual yield, is the simple interest rate that would yield the same future value over 1 year as a particular compound interest rate. Note that we often call the compound interest rate the nominal rate, right? So that's just a new word. So what this is saying is it's going to convert a compound interest to a simple interest rate for a 1-year term. But remember that after 1 year, a simple interest and a compounded annually interest rate are the same thing. Right? So here's the formula. It's just 1 plus r over n to the n power minus 1, and that allows us to calculate or to compare interest rates directly. So here we've got a loan has a nominal interest rate of 4%, and the interest is compounded weekly. Would you expect the effective interest rate to be higher or lower than 4%? I would expect it to be higher, right? We know it's going to be higher because the more often we compound, the more we earn. So we're going to calculate the effective interest rate. Notice if it's weekly, there are 52 weeks in a year. Our nominal or compound interest rate is 0.4, and that's actually all we need to calculate the effective interest rate. So this is 1 plus 0.04 over 52 raised to the 52 power minus 1. I'm going to smash that in Desmos. 1 plus 52, nope, 0.04 divided by 52 raised to the 52 power minus 1. All right, it's 0.04079. In other words, it's a 4.079% interest rate. What this means is after 1 year, if we were earning compound interest compounded weekly, we'd have the same amount of money in our bank account if we were earning 4.079% simple interest in a 1-year term. How are we all doing on this? You all doing okay? Surviving. Okay. All right. Okay, so let's try this. Find the future value after 1 year for investment of 10,000 at 4% compounded weekly. Well, recall that future value is A equals P times 1 plus R over N to the NT. And here our formula is 10,000, or our stuff is the P is 10,000. The interest rate is 0.04. It's compounded weekly, so that's 52. We're raising it to the 52nd power, and year is 1. If you look at this piece of the formula, this piece is exactly the same piece as this piece. We just didn't subtract the 1. So let's do this calculation. I already hit it in here, so I'm just gonna leave that there, and I'm gonna put in my 10,000. Okay, so I get 10,407. 407.94777. 9477705. Huh. Seems interesting. The author says, hey, go ahead and divide that number by 10. What do we notice? So I'm going to go back to Desmos. I'll just put parentheses around that whole mess. Divided by 10,000. I mean, oh, wait a minute. We get 1.4 fail. 1.0407947705. Wait, what? It's the same thing, right? This is the growth factor that we learned back in Unit 2, and the growth rate is this percent when we subtract 1 from it. Isn't that beautiful? Okay, so what's the point of this? Well, here, why don't you try this? Calculate the effective interest rate between these two things. So let me write down the information we've got. We got 6.2% is the R, and the N is 365. That's daily. So get me the effective rate for that. And then over here, we got R equals 6.25%, and it's compounded semi-annually, which is 2. So calculate which one's better as a savings account. In other words, actually use the effective interest rate and calculate the effective interest rates for these two. I'll give you 5 minutes. Set a timer. Okay, set a timer for 5 minutes. Yeah, thanks. Anyone get the effective rate? Rates, I should say. So you calculate the first one. Fail. And that's how you get the second one. From there, it's a matter of, can you type? Which these are a little tricky to type in, especially with the exponents. And I don't know, I'm kind of assuming you all are okay with typing in exponents. 6, 3, 9, 5, 6, 6, 3, 9, 5, 6, 6. Please let me know if you all need help typing these in. Yeah, the one was 1 plus 0.0625. Notice I screwed up with the parentheses. You've got to have those parentheses around them because we're raising the sum to the second power. Uh, 0.066262. 0.066262. So in terms of their interest rates, this one is 6.396%. This one is 6.626%. All right. So which is the better savings option? Surprise, surprise. It is this one is better because it has a higher interest rate. Now, if I'd said, which is the better loan option, we would say the other one because the interest is lower, right? So when you borrow money, you want lower interest. When you're saving or investing money, you want higher interest. Is that okay for you all? Does anyone have any questions?
My numbers are different for the second one. I think you mistyped yours, I think.
Yeah, I did. It should be 2.5. Nailed it. Thank you. Ooh, does it change the answer? It does. Look at that. Surprise, surprise. I am wrong. I did that on purpose just to see if y'all were paying attention. I swear. But only by the moon and the stars that are in the sky. I don't know if I'll be there, but I'll try. Okay, so what was that? 0.06, 63, 47, 66. 63, 47, 66. So the interest rate is 6.348 if I round it to whatever those amounts of decimal places. So I was wrong. This is better. Higher interest rate. Excellent, excellent. Thank you, Jennifer. Okay, this leads us to a final concept, and that is, what if interest were compounded continuously? That means, what if our n was infinite? It's just always being compounded. Now, the author takes us through some stuff here, and it gets a little crazy. And basically, you're being asked to do some calculus. So I'm just going to have us look at this thing, and I'm not going to talk through how all of this goes together. I think it's a little bit beyond the scope of this course. And what I'm going to do is in Desmos, I'm going to type 1 plus 1 over x to the x power, right? And we're just going to see what happens to this. So we'll jump into Desmos, and I think it's time for a new graph. So I'm going to get a new blank graph, and we'll start with our expression f of x equals 1 plus 1 divided by x raised to the x power. And then I'm going to smash in a table here, and I want this to be f of x1. And then we're going to put in our values: 50, 100, 500, 1500, yeah, so 500, 1000, I think, 1500, 2000, and then 2500. So you're supposed to notice what's happening to this. Look at these numbers. They seem to be approaching a particular number. In fact, if we were to look at the graph, you could see that there is a number this is approaching. So if I kept putting numbers in here, 5,000, 10,000, 20,000, you see that the number becomes the same thing. And what is that number? It's E. You're like, what? E's a number? Yeah, it's a number. It's 2.718281882846. It goes on forever and ever. It's a number like pi, meaning it's an irrational number. It's a special number that we've discovered occurs in the natural world. And this number, this letter that we've called it, is used for compounded continuously interest. So I'm just going to write down what this formula is. The compounded continuously formula is A equals P times E raised to the RT. That's the compounded continuously formula. It turns out this isn't really used much in banking, like in financial markets or financial stuff. It does happen to model radioactive decay really well. So like in Chernobyl, where the power plant blew up, we can model how much time it will take. We can figure out how much time it'll take for the radioactive material to be gone. It's used in carbon dating because we know how fast carbon decays over time. So it's just another form of the compound interest formula. We are going to do calculations with money with it, even though it doesn't really happen. And what you're looking for is this word continuously. Anytime you see that, you know you're dealing with this. So we're going to compare the simple interest rate with the compound interest rate, where we've invested 50,000 at 6% interest. So I'm going to write these two formulas out. So the simple interest, I'm going to call f of x. That's going to be 50,000 times 1 plus 0.06 times x. And then the g of x is going to be this compounded continuously rate. So this is going to be 50,000 times e raised to the 0.06x. And we're just going to compare these two amounts and see, you know, what happens over time. How awesome is compounded continuously? Is it really all that awesome? By the way, this is the maximum amount you can earn with compounded n times per year, right? Like this is the most amount of compounding you can do. Okay, there's the simple interest one. Oops, no, let me put in my g of x. GR of x. There's that one, and then we want our table. And let's see, I'll do f of x1 and g of x. Oops, don't capitalize, g of x1. And then we want to calculate the difference between these two, just to really compare what's going on. G of x1 minus f of x1. Okay, so we were supposed to do 5. Yep, that's 5. 5, 10, 15, 20, 25, and 30. Okay, so remember, these are future values, and then these are a difference in the future values. So it's a huge difference between simple interest and compounded continuously. You know, in the first 5 years, it's an extra $2,400, but in the next 5 years, it's an extra 11,000, and then it's an extra 27,000. I mean, this is a really big difference. 162,000, right? After 30 years, I might make it to that. What am I, 40? I might make it to 70. I should be able to, right? So that's a nice extra amount of earnings. And this is the best you can get in terms of extra compounds per year. It's the cap out. Okay, I'm guessing it's hard to know where you all are at, because I've probably like gone too fast and you all are like blown out of the water. Maybe not. Maybe it all made total sense. So let's check. First, let's do the lesson check before we do anything else. And then we'll pull up the worksheet and see if you all got it. So the 3-2 lesson check, which is due November 1st, apparently. I'm going to quick make it so you can do infinite attempts for at least this class. I need to fix it for the other class. Preview. Answer question 15. Find the future value after 20 years, round to 22 decimal places. So we're looking at the future value number 15, this one, which we didn't do. So let's do it together. So note it's compounded continuously. So we're going to use that P times E raised to the RT. So we're looking at 5,000 times E to the 0.04 times 20. E, oops, E, I put 3, 5,000 E raised to the 0.04 times, ooh, look, it dropped it into the denominator. So I'm gonna need to put parentheses up here, times 20 to get it right. 11,127.70 is our answer there. 11,127.70. Oops, wrong spot. Nope, that was the right spot. So 11,127.70. Submit. Did I get it wrong? I did get it wrong. Why did I get it wrong? Must be a problem with the answer. Why won't this let me look at it? This dumb thing. There we go. Okay, we must be looking at the wrong one. Wrong question, or maybe it changed it. There we go. Now we got it right. Okay, how do y'all feel about that? I changed it so it had the right answer in there. I think the textbook changed the problem. I gotta change it in both classes. I got 2 classes here meeting, so let me make sure I get that all set up. Okay. Actually, before I put you loose on the worksheet practice, let's write up all the formulas we just learned. So for compound interest, oh, the answer, it was this. Oops. This is lesson check 3.2, 11,127.70. You are most welcome. Okay, so from this lesson, here's all the simple interest formulas. For compound interest, we have, we really just have 3.
Every time I try to submit the answer, it keeps telling me it's wrong.
Me too.
Did y'all click refresh?
Yeah,
Yeah.
Did I click save?
I don't know. I've done it like 4 times now.
Let's see, how fast, did I click save? Well, look, I didn't click save. Oh, well, that was 3-1. Okay, let's see here. Oh, I didn't click save. You all must be in the I4 class. Try it now. Sorry, that's really annoying, isn't it?
It's doing the same thing for me.
Yeah, maybe I didn't. Let's see what I did.
It worked for me this time.
Okay, so then it must be the other class. I didn't click save or something. Wait for it. Yep, didn't save it. Okay, it should work for everyone now. Let me know if it's still not working. Okay, so I'm going to write down the 3 future value formulas that we had for the compound interest. The first one is the least useful one because it's a very specific one. This is compounded annually, meaning n equals 1. The second one is the same thing. It's just now n is not equal to 1. So this is n compounds per year. And then the third one is totally different than those 2. It's the compounded continuously. Now, for all three of these, if we want to calculate the amount of interest earned, we can't calculate directly. We have to do this. And then we have to say, well, the interest we earn, the amount of money that was given to us is simply whatever the future value is minus the initial amount we invested. That's that. This is the equivalent of our I formula up here, this one. And we aren't going to be able to do these things because you'd have to know logarithms to do it. So and with compound interest, it's quite complicated to solve for P or R or T in any of these formulas. So we just don't do it. And then finally, we talked about the effective interest rate, which is a way to compare different in compounds per year, not the compounded continuous one, although there is one that we could, there is a formula for it, we just don't talk about it. So the effective interest rate was this E equals 1 plus R over N, what? Yeah, raised to the N power minus 1. And this is attached to or useful for this one, all right? Not this one. So it's only good for comparing these values. So those are the new formulas for compound interest. If you look at the amount of formulas we have so far, it's a lot, right? And a lot of the challenges you're going to face in the worksheets and on the final exam and even in your project is determining, hey, which formula do I need to use and when do I need to use it? So let's try that. Let me see if I can find the worksheet thing I want you to look at, and I'll give you a few minutes to attempt it, and then we'll talk through your answer. So the first worksheet, the 3-2 worksheet, here it is just a bunch of different calculations, all right? Yeah, so let me give you 5 minutes to try number 1. And I will put these, I probably wrote these a little too fast. I will put these back up just in case you need to see them still, compound interest formulas. All right. Set a timer for 5 minutes. That was 5 minutes. Anyone get any of these answers? Or do you need more time? Or are you stuck? Or are you just done with this and ready to leave?
I think I got continuously
What'd you get?
23,900 or 900 or 23 million, I think. 916,445.26.
Right. So I'm like, hey, what'd you get? And then I don't even know the answer. So you're rattling this off, and I'm like, man, that was a jerk of me to tell you to say it and not even know the answer. Okay. Probably. Maybe. Let me see. This is what I got. I should mention that we're doing what I found was the future value.
I didn't put the I did 1.98, not 0.0198.
Nice. By doing that, you know how much you were earning?
A lot.
198% interest. Yeah, that's beautiful. Yes. Good. I'm glad you made that mistake, because that is a common mistake, and it's good to highlight that for everyone. Yeah. Oh, that's amazing. That's the interest we want to earn, but that's called a Ponzi scheme is what that's called. Earning that much interest. Excellent. Okay. Let's see. So, Jennifer, you said you got monthly. Oops. Come on. 1 plus 0.0218 divided by 12 raised to the 12 times 5. That would be the monthly. Maybe we can do a little bit of this mess. There we go. And then the simple interest, we just have to use that simple interest formula in terms of future value. So that would be the 12,000. There's 2 ways we could do it. The one we've been using today is the 1 plus the R times the number of years. That. Does that look like what you all got? Let me get rid of this one because that's nothing. And let me get rid of these. So there's the 3 ones. Continuously first, monthly second, simple third. And these are all future values. If we want interest, we could subtract 12,000 from all of these. And that would get us the amount of interest earned. And that might make it easier to compare the two. Okay, no worries. Does it surprise you that the simple interest is the best option and kind of by far? Like you make an extra $600 with that one.
To me, that is surprising because I would think that continuously would be more.
Yeah. It is a much smaller interest rate. Really, there's only 1% difference. Yeah. Okay, so if you keep these all in here, question 2 says, all right, let's flip the switch here. And what happens after 50 years? Keep everything the same and then do 50. So that just means I'm going to put a 50 in each one of these spots. Now look at which one's best. So when we give it a little more time, the compound interest ones outperform the simple interest ones. And that is always going to be true. Given enough time, no matter how big a difference the interest rates are, compound interest will win every single time. because you're earning interest on interest, where simple interest is a fixed amount every single time. Okay, any questions on these? I'm just gonna leave these for you to finish up. Maybe should I even hide this? Whoops, they're gone, and let you practice that calculating. Note the key is noting, excuse me, connecting the words with which equation you should be using. And there's a lot to pick from. This is just straight up calculate an effective rate. The trick here is figuring out how many times you're going to compound per year if it's being compounded hourly. So my hint, I'm just going to give you a hint. You need to figure out how many hours are in a year. So I'm going to say N equals number of hours in 1 year. And I'm going to let you do some work to figure that out. So, what do y'all want to do? Do you want to try these things and then check your answers? Are you happy with where you're at and ready to go take a break? Have a great weekend. Are you focused on the midterm? Does anyone have any questions for me? Anything? I've decided that I've covered what I want to cover for today, but I'm happy to go over, like, check your work from what you've done here. Okay, so you tell me when you're ready to check your answers on whichever question you're working on. You just tell me, Jennifer, when you're ready to check, or anyone.
Okay, I'm ready to check my answers, but I'm stuck on number 3. Also, I think you're muted still.
Okay, here's number 2. Thank you. So here's number 2 in terms of the amount of interest earned. These are not the future values. If I delete this 12,000 part, you get the future value between each. So it doesn't particularly, you're not told what you have to calculate. Your job is to find which one's better. So you can compare future values, you can compare amount of interest earned, it's up to you. Was that matching what you all got?
Yeah, that's exactly what I got for all of them.
Nice. Nice. So the compounded monthly is best.
Yep.
Good. So the effective interest rate, let's see, how many hours did you get in a year?
Let me 8,760.
I agree. So that's our N. So we're going to do 1 plus 0.0735 divided by 8,760 raised to the 8,760 minus 1. So 0.076268 or 7.63%. Now, what is this? This is 7.63% simple interest. Is that what you got?
I honestly didn't even know how to attempt it. So yeah, I didn't have anything.
Nice. Okay, ignore that. You don't get to see that. So here's how I knew to do that. It said effective rate.
Okay, so effective rate, it would be simple interest then?
Well, so to find the effective rate, you use the effective interest rate formula. And what that finds, so this is that formula. What that finds is an equivalent 1-year simple interest rate.
Okay. All right, that makes sense now.
Good. What was part B of that? Compare, contrast, simple and compound interest. Okay, I'll let you all have fun with that one. So if we were to like make it clear what these two are, what we could do is do a simple interest. Let's invest $1,000 for 1 year. So there's that one. And then $1,000 times 1 plus 0.0735 divided by 8760 raised to the 8760. There we get the same amount of money when rounded to 1 decimal place. If we added more decimals on this one, like if we did the 268, we get even closer.
Okay.
So that's what the effective interest rate does. Cool.
So then, okay, for the compound interest, I guess I don't know, it's still on.
Talk to me.
Yeah, I'm lost. So the compound